Can a tangled mess of lines make sense? Welcome to the magic of spanning trees. Imagine you have a network like a city map with roads connecting different locations. A spanning tree is like choosing the simplest set of roads that connects every location without any loops. Think of it this way. Spanning trees are connected, meaning you can get from any point A to point B. They have no cycles, so there's no way to loop back on the same path. They also use the minimum number of roads needed to connect all spots. And they span, yes, they touch every location on the map. We have different types. Minimum spanning trees, MST, use the least total weight. Random spanning trees are, well, random. DFS spanning trees come from depth-first search. To find them, we use algorithms like Kruskal's, Prim's, and Boruvka's, each with its own nifty method. Applications. They help in network design, data aggregation, clustering, and even social network analysis. So next time you see a graph, remember, spanning trees are the unsung heroes bringing order to chaos. A scene opens with a classroom setting. The teacher stands in front of a whiteboard filled with diagrams of graphs and spanning trees. Students are seated, attentively watching and taking notes. Teacher: all right, class, today we're diving into the intriguing world of spanning trees. Teacher draws a simple graph with nodes and edges on the whiteboard. Can anyone tell me what a spanning tree is? Student raises hand. Student: isn't it like a way to connect all the points in a network without any loops? Teacher: exactly. A spanning tree connects all the nodes without forming any cycles. Teacher highlights a spanning tree on the graph. Now, why is this important? Think of our city map analogy. If you want to travel from one point to another, you need a clear and direct route, right? No unnecessary detours. The camera focuses on the whiteboard as the teacher draws different types of spanning trees. Teacher: we have various types of spanning trees. For example, a minimum spanning tree, or MST, uses the least total weight. Imagine it as the shortest and most efficient set of roads connecting all locations. Then we have random spanning trees, which are, well, random. And DFS spanning trees, which come from depth-first search. Student looks curious and raises hand. Student: how do we find these spanning trees? Teacher: great question. We use algorithms like Kruskal's, Prim's, and Boruvka's. Each has its own unique method. For instance, Kruskal's algorithm sorts all the edges and adds them one by one, ensuring there are no cycles. Prim's algorithm, on the other hand, grows the tree by adding the smallest edge connecting a new node. The camera cuts to students nodding and taking notes. Teacher: applications of spanning trees are vast. They help in network design, data aggregation, clustering, and